Okay, so today we're going to start talking about resting membrane potential. Resting membrane potential is the separation of charges across a cell membrane. So if we have a cell membrane here, like this, the resting membrane potential would be the difference of the charge of the ECF versus the ICF. So this is mainly established by pumping ions across. So the two big players of resting membrane potential are potassium, which has a high concentration inside the cell and a low concentration outside the cell, and sodium, which is opposite. It has a high concentration outside and a low concentration inside the cell. And the way we establish resting membrane potential is through the sodium-potassium pump. The sodium-potassium pump is an intermembrane protein that will take and it will pump three sodiums out of the cell for every two potassiums pumped into the cell. So that is what creates these concentration gradients. This pump will pump potassium in and sodium out at a ratio of 3 sodiums to 2 potassiums. Now the other way that the resting membrane potential is established and maintained is through leak channels. So this has to do with the permeability of a certain ion to a cell membrane. If a certain ion is more permeable to a cell membrane, it probably has more channels in that cell membrane to allow it to flow through. So potassium, it is much more permeable to the cell membrane than sodium is. So we'll just represent that with two leak channels here. And these leak channels, they allow potassium to flow out of the cell down its concentration gradient. And we'll represent the sodium leak channel right here, like this, which allows sodium to flow into the cell. Now, as potassium leaves, it'll leave at a higher rate than sodium will. And as it's leaving, it will leave behind proteins inside the cell. And a lot of these proteins that help establish this resting membrane potential are negatively charged proteins, and it leaves anions behind. So we'll just put An minus, so anions, and it leaves those behind. Because potassium being positively charged is moved across the membrane and leaves negatives behind, it leaves a negative charge on the inside of the cell membrane, and it brings a positive charge to the outside of the cell membrane. And we call this charge, the separation of the charges, resting membrane potential. Now, every cell in the body has a different resting membrane potential, but for today we will look at neurons, and so the resting membrane potential we'll deal with is negative 70 millivolts. Things that can affect resting membrane potential, we'll draw a little graph right over here, a couple of them. So let's talk about how concentration and permeability can change it. So we'll have these coming out here at a resting membrane potential of about negative 70 millivolts. Now, if we had hyperkalemia, or a high concentration of potassium outside the cell. So instead of a smaller, we'll have a slightly bigger potassium concentration out there. Now what does this do? This takes this concentration gradient that we had and it lessens that concentration gradient. Meaning less potassium will want to flow across the membrane, leaving less negatives behind, which means the inside of the cell would become less negatively charged. This would result in what we call depolarization. So the resting membrane potential would take and correct itself towards zero, or depolarize, become closer to a zero charge. Then if we do the opposite and we have hypokalemia, and we take this potassium and we make it really small concentration outside the cell. What that's going to do is it's going to do the opposite. It's going to increase this concentration gradient, and it's really going to pump potassiums across. Doing this would have the opposite effect, and it would hyperpolarize. So we have depolarization and hyperpolarization. So we depolarize and we would hyperpolarize. Now let's look at what would happen if we would take and add another sodium channel here. So over here, we're going to go ahead and we're going to make this more permeable to sodium. Sodium will come through, and it will now be able to flow better down its concentration gradient. And because of that, we're introducing more positive charges into the ICF. So we're going to add some more positive charges into the ICF. Thus, we will have a depolarization event where the resting membrane potential will increase towards zero. So we're just going to say increased permeability to sodium. We're going to have a depolarization. Okay, and those are some of the ways that we can change resting membrane potential. So the next thing with resting membrane potential is there are ways that we can try to determine a certain cell's resting membrane potential. And the way we do this is through the Nernst equation. This equation is equal to negative 61.5 over Z log base 10 of the concentration outside the cell over inside the cell. No, wait. Inside over outside. I'm going to have it inside over outside. Okay, and this Z right here, that is just, so Z is the charge of the ion. Okay, ion charge. So the Nernst equation gives us what the resting membrane potential if a cell was only permeable to one ion. So if we wanted to figure out if a cell was only permeable to sodium, we would use the Nernst equation to figure out what its resting membrane potential would be. So if we take and we do this for something like potassium, let's just keep on the potassium train. So you have E is equal to negative 61.5 over 1, because sodium and potassium, they both have a positive 1 charge, but potassium, positive 1, log, and let's say the inside concentration is 140. We have 140 over outside 5. Okay, so if we plug this into our calculator, we have negative 61.5 over 1. Then we do the log of 140 over 5. And that would give us a Nernst potential of negative 89. So, if these were the concentrations inside the cell and outside the cell, and we had a cell only permeable to potassium, its resting membrane potential would be at negative 89 millivolts. However, we know that the cells are permeable to things other than potassium. This leads us into driving force. So driving force is the resting membrane potential minus the Nernst potential. So this will tell us where ions will flow when channels are open, right? So if we were to draw a cell over here, the driving force would always be inside the cell. So this example, we have a driving force. We have a resting membrane potential of negative 70. And then we're going to subtract a negative 89. All right. So when we do the math, that driving force would equal 19. So we go ahead and we put a positive 19 driving force for potassium inside the cell. And because potassium has a positive 1 charge, we can think of it as this potassium is going to be repelled by its driving force. So if we have a channel that opens, potassium will flood out of the cell. And it's the same for other things. If we were to take the Nernst potential for sodium or other things, we would be able to place that driving force in the cell and see which way those ions would move. All right. So now we are going to switch gears and we are going to look at action potentials. So an action potential is the signals that we send through our cells. So neurons, it's how we send signals through a neuron. So how we do this is we can pull up our little graph again. It comes in different stages. So I'm going to draw a big graph here. And we're coming out negative 70 here, do 0 here, we'll do 30 there. So it's coming out negative 70. At some point, we'll have a stimulus introduced. That stimulus is going to open some sort of gate in a neuron or in a cell that's going to allow for a change in this resting membrane potential. So let me add a little red dotted line here. Okay. So if that stimulus depolarizes the cell, it's going to start moving up. Then once it hits this red line, we're going to see it peak, come back down, and then do that. So this is an action potential. So we're looking at this. We have this step 1 right here. That's just resting membrane potential. So 1 is resting membrane potential. 2. So here we have 2, and 2 is going to be some sort of stimulus that will depolarize the cell. So we're going to open some sort of gate in a neuron and allow something to flow in that will begin depolarizing this neuron, the cell. So we're going to we're going to depolarize. Okay, this 3 right here, 3 is really important because 3 is what we call threshold. So 3 is threshold. Threshold is where the action potential really gets going. At threshold, we have sodium voltage gated channels. So we have a membrane here. Let's go down here. We have a membrane here. And in this membrane, right here, we have a channel. And it looks something like this. It comes down, this comes down. We have a gate here. We have this other thing here, and we have this. Now, at resting membrane potential, this is inactive. But as we depolarize the cell, we have a bunch of negative charges in here and positives in here, out here. We begin to get rid of some of these and some of these and some of these. We're approaching a net zero charge here. And this subunit right here is positively charged. So at resting membrane potential, it's being pushed down. But as this depolarizes, it's able to open this gate, and this springs up. So this is going to spring up and open that gate there. This allows sodium to flood into the cell. That is what happens at threshold. At threshold, we get this voltage gated sodium channel open. So I'm just going to draw that right here. An open voltage gated sodium channel, right? But also at threshold, we have voltage gated potassium channels. They're also here on the membrane. And they also begin to open. They don't open as fast as the sodium ones. They're a little slower. So we're going to draw that here as it begins to open. So during this depolarization phase, where we have the big jump, these sodium gated channels, the sodium channels, they are wide open. But they're only open for a very short amount of time. So as we depolarize, they have the deactivation gate that will come in and they will shut this channel. So they begin to look like this. They'll have another conformational change and this ball will come up and it will close that. This stops the sodium from flowing into the cell here. And as that happens, these potassium channels, they continue to open. And as they open, they allow potassium to flow into the cell. Out of the cell. Flow out of the cell. And that's what we hit our peak here. And at that point, these sodium gated channels, they're closed with that deactivation gate. And these potassium ones are open, allowing that potassium to flow out and try to reestablish this resting membrane potential. And we see it begin to depolarize again, or I guess repolarize. We see it begin to repolarize. And as it repolarizes, these gates remain open. And at this same line here, this same charge, membrane potential charge, there, we get the sodium channels, they go through another conformational shift and they close again. That deactivation gate disengages and the activation gate can become fully activated again. And the potassium channels, they begin to close, but they are slower, so they lag behind a little bit. And they allow more potassium to leave the cell, which is what we call hyperpolarization. We go past resting membrane potential, and then as sodium leak channels, because down here at hyperpolarization, these potassium channels, they close. So at this point, the potassium leak channels will allow potassium to leak out and sodium to leak in, and they reestablish resting membrane potential. Now, there's certain types of so with an action potential, we can only do an action potential when we have the resting membrane potential needed for the action potential to be propagated. So at this point right here, after we hit threshold and until we hyperpolarized, that is what we call an absolute refractory period. During this time, we can't propagate another action potential. Doesn't matter how big the stimulus is, what we add to it, we cannot send another action potential at this point. However, down here where we are hyperpolarized, this is what is called the relative refractory period. At relative refractory period, we can send another action potential because we're below threshold. However, it takes a larger stimulus to send that action potential. So a higher stimulus to send that action potential. Now there's a couple different types of potentials. We have the action potential, and then we have a graded potential. So during an action potential, like I said, it is one and done. You hit threshold, you have an action potential. You're sending that action potential and it's going. Graded potentials, they can add on to each other. So you can think of it as an action potential, like we just mentioned. You have this, you hit that threshold, you are sending a signal, it's going. Graded potentials, however, if we were to draw the same graph, they're like little bumps that never reach threshold. But if you have enough of them, you can hit threshold and send that action potential. They're like waves when you throw a pebble into a pond. You have that, and then it goes out, and it goes out, and it goes out. And the farther out you get, the weaker it is. But you can add more waves. That's a graded potential. You can send it out and it'll get weaker as it goes, but they are still potentials. You are depolarizing that membrane ever so slightly. And then the last thing, so we want to look at let's look at an example of an action potential in drawing. So we have a neuron. It comes down and it synapses with another neuron. So we'll have this one come out. So this synapse right here, this is the soma. Here, at the beginning of the axon right here, we have a voltage gated sodium channel. Now, this is what is called the axon hillock. So what happens is as an action potential, we'll just draw it like this, comes down, this one, it will reach the end here and release neurotransmitters. Now, as those neural transmitters come out, they bind to gates here in the postsynaptic neuron. So as they bind to these gates, the gates are usually ligand or voltage gated, but if it's ligand gated, they will open with the attachment of one of those, and they'll allow a positive charge, calcium, sodium, some sort of positive charge to flow into the cell. As that flows in, it leaves a positive in the cell, and as we know, the inside of the cell is usually negatively charged all the way across on the inside due to that resting membrane potential. And as this positive charge gets it creates an electric field that goes through the neuron. And if this is strong enough, or there's enough that summate and add to each other in here to reach this axon hillock, it will change. It will have an effect on this voltage gated sodium channel. In turn, opening it here and allowing sodium to flow into the cell. And where sodium is a positive charge, it will do the same thing, and it'll activate another channel here, allowing sodium to flow in, and so on and so forth down the line. And that's how we propagate an action potential down a neuron. There are certain things that will affect how an action potential moves down a neuron though. One of those is capacitance and a length constant. So if we look at a neuron here, we're just going to draw the axon part of it. We have leak channels going through here, allowing things to leak out on both sides. We're leaking. So we have negative charges on the inside here, and with those negatives, we have positives on the outside. So we're just gonna draw a bunch of positives out here and out here. So capacitance is the charges per volt along a membrane. So if we know that we're at negative 70 millivolts, there are more charges here per volt. So if we say, let's say there's 70 charges per 70 millivolts, that comes out to be 1. That is the capacitance of 1. But if we were to add something or some way for these charges to not interact as much, not be as interactive, and say we went down to 45 per 70, we'd get 0.5. So that is the idea of myelin. Myelin comes in on the membrane, on the cell, and it makes it so that there are less negatives interacting with the positives on the outside. This allows for more leakage from the cell because you're not having this push-pull. So if we were to have a positive charge in here that was trying to leak out, it would be pushed away by these positives but pulled back in with those negatives, and it could come back in. However, here we have the same positive charge leak out. There's a lot less acting on it here, so it might actually make it out. That's the idea of capacitance. And as far as length constant goes, so like I said, capacitance is equal to charges per volt. Our length constant, tau, is equal to the square root of the membrane resistance over the internal resistance. So, membrane resistance is how well the cell membrane stops things from flowing. So, a high membrane resistance means it's like this. There's not going to be a lot of leakage across. There's not going to be a lot of charges going over and out. So if we have a high membrane resistance and a low internal resistance, which an internal resistance are things on the inside that could possibly block an action potential. So if we have proteins in here or other ions, those kind of things, that would be a high internal resistance because there's a lot of things that can absorb the charges in the electric field during an action potential. So if we were to have a low internal resistance and a high external resistance, that means that the effect that this has will travel farther. It'll have a farther length. However, with myelin, what happens is we decrease this here, so our length constant goes down. Now, this allows us to make things travel faster, but they also won't travel as far. So when you have things where things become unmyelinated and it's not able to send it as far, sometimes if you were to get rid of one thing of myelin here and we had another one coming out here and here, instead of, because there's no sodium gated channels here or here, in order for this action potential to reach over here, it would have to go all from the end of this myelin sheath to the beginning of this one, or where this one ended. And that's a lot harder to do with all of this resistance across the membrane. So what we do with myelin is we decrease the membrane resistance to allow that to travel better and to travel